a Portland Community College Mathematics telecourse, a course in arithmetic review produced at Portland Community College. Let's begin this lesson with a couple of very basic properties of fractions. The first one is an act we will call fraction building. It states that one may multiply both the numerator and the denominator by the same amount except 0. The fraction's form will change by doing this, but not its value. Equivalent fractions are fractions that are different names or forms for the same number value. Now let's take an example. Let's presume that this total rectangle stands for the number 1, or 1 whole. Now if we were trying to determine what fractional part of the whole is shaded in, it depends on how we look at our subdivisions. If we only look at the large 3 subdivisions, then we have shaded 1 part out of 3. See, 1 part out of 3. But if we concentrate on each of these vertical strips alone, then we would say I have shaded in 2 vertical strips out of 6. 2 out of 6. On the other hand, if we concentrated on the very tiny squares, then we would say we have shaded in 6 small parts out of a total of 18 of those small parts. But relative to the whole, the same portion has been shaded. So we call these 3 fractional expressions equivalent fractions. Now notice, we could have got from these two to this by simply reducing. What we are going to discuss, fraction building, is the reverse, going from a reduced form or any form to a form that's built from this by multiplying top and bottom by the same number. Notice, by using that definition of fraction building, I can transform this form to this form by simply multiplying top and bottom by the number 2. This process we call fraction building. Now note logically what's really happening here. I'm really multiplying 1/3 by the new fraction 2 over 2. And 2 over 2 is 1, and 1 times anything doesn't change it, although it certainly changed. Now if I wish, I could change the same starting fraction to its equivalent form 6/18 by multiplying top and bottom by 6, and I get this. So our fraction building rule says I can multiply top and bottom of a fraction anytime I want by any non-zero number I want. For instance, what if I wanted to change the fraction 1/3 into another form of the same fraction, which would have a denominator of 24? Then the question merely becomes, since this denominator changed to 24, what would I multiply 3 by to get 24? And of course the answer to that question is 8. But the fraction building law says, fine, multiply it by 8, providing you multiply the top by 8. And of course that gives me 8 on top and 24 on the bottom. So the fraction 1/3, 2 6, 8 24s, 6 18s are all equivalent fractions. That is, even though they look different, they all have equal value. So your practice work in this exercise is to simply get you used to that simple idea. this case, we like to build this fraction so that instead of a denominator of 9, it has a denominator of 27. So you simply ask, what would I have to multiply 9 by to get 27? Or if you wish, 9 into 27 is 3 times. But the fraction building law says you may multiply the bottom by anything, providing you multiply the top by the same thing. So my fraction 21/27 is equivalent to 7/9. It has the same value even though it changes its form. Now in this case, it's the numerator that directs our attention. We ask, what would I multiply the 6 by to get 48? Well, that's 8. Well, our fraction building law says if that's what you're going to do, then multiply the bottom by 8 too. So the question mark is 88. So 48 88s and 6 11s are in fact the same fraction. Let's see how we would approach this problem. Our task is to build the fractions 1/12, 3/4, and 5/6 into equivalent fractions, but such that they all have the same denominator. Now the question really is going to reduce to this. What number is divisible by 12, 4, and 6? Certainly it has to be 12 or larger, since 12 is the smallest number divisible by 12. Now this is simple enough, it won't take too much thinking to realize that the number is. Let's make a note of that. 12 is the lowest number that all three of these will go into. In fact, 12 will divide into 12 once, 4 goes into 12 3 times, and 6 goes into 12 twice. But our fraction building law says if I multiply the bottom or the top by anything, I must multiply the other member of the fraction by the same amount. So I'll multiply top and bottom here by 1, which is the same thing as leaving it alone. That gives me 1/12. Top and bottom here by 3, which gives me 9/12. And top and bottom here by 2, which gives me 10/12. Now these two fractions are equivalent. They're the same fraction. So are these two equivalent to each other, and these two. But now I started with 3 fractions that had different denominators. I have the same 3 fractions in value now, but they all have a common denominator. Now as it turns out, these 3 denominators would have also divided into 24, 36, and many others. 12 happens to be the smallest number. So had we asked what smallest number is divisible by those 3 numbers, do you realize that's the same thing as asking what is the least common multiple of 12, 4, and 6? And that's, of course, the whole gist of our Chapter 2 lessons. And we're about to dip back and use that information once again. Let's do one more problem focusing on that terminology. Find the lowest common multiple of these denominators, and then build each fraction so that it has the lowest common multiple as the common denominator. So our first question is, what's the least common multiple of those 3 numbers? And it turns out to be 42. 6 goes into 42 7 times. 7 goes into 42 6 times. And 21 goes into 42 twice. But now our fraction building law says I can multiply top and bottom by the same thing anytime, anywhere I wish. So therefore, transforming these 3 fractions, this one becomes 7/42, This one becomes 18, 40 seconds again, and this one becomes 10, 40 seconds. So now these three original fractions have equivalent values but different forms, and specifically forms which have a common denominator, and specifically the least common denominator. This particular skill is all important for the next few lessons, so learn it very well. Now let's watch and listen very carefully to the progression of problems from this very simple one to the one we'll conclude with in just a few moments. First, the fraction building law stated that I can multiply top and bottom by the same non-zero amount, and even though the fraction will change how it looks, that is, its form, its value will not change. We call those equivalent fractions. And we started our exercises by giving you a new form where the bottom has been supplied, but the top has not. So we ask, what would this be in order to be sure that the fractions are equivalent? And our process was simply this. Divide this into this, that's 3 times, and that tells me I'd have to multiply this by 3 to change it into this. But the fraction building law says, fine, multiply by anything you want, providing you multiply the top by the same amount. And that's a very important proviso. They must be the same amount. And of course, multiplying the new tops now, we get 15. So our claim is that 5, 6, and 15/18 are precisely the same fraction. Now, of course, if you were to reduce this, it'd go right back to 5, 6. So you can see fraction building is sort of the inverse operation of reducing, isn't it? Now, here is a different fraction. This fraction is not equal to that fraction. However, could I change it into an equivalent form so that it will have the same denominator as this one up here? That is, can I change both of these, even though they're different fractions, into equivalent forms whose denominators will nevertheless be the same? And of course, since they are different fractions, their numerators will have to be quite different. So we simply ask, 9 goes into 18 how many times? That's 2. But the fraction building law says, fine, multiply the top by 2 as well. And of course, this product would give me 4 over 18. So we now have 2 fractions who, even though they are not the same, because we can just see 15/18 is a lot bigger than 4/18, but nevertheless, we were able to produce 2 fractions which have the same denominator. And that's to be the goal of this and future lessons. Then we complicated the question by just a small amount. Here I have 2 different fractions. I could build this fraction so it has all sorts of different denominators, or numerators for that matter, and so could I here. And most of those denominators would not be the same. But our question is, could I possibly build each of these to a fraction where at least their denominators will be the same? And that boiled down to this simple question. Look at these 2 denominators and ask, what number will both of them divide into? Preferably the lowest. That will give us the least future work. And hopefully we would see it's 24. By asking the question, what will both of these divide into each, we're stating that I can build this into 24s and this as well into 24s, so indeed they end up having common denominators. So looking at the first fraction, we can see that 6 divides into 24 4 times. Our fraction building law says fine, just make sure you multiply top and bottom by the same amount. And that gives me 20 24ths. So this fraction and this fraction are equivalent. They certainly don't look alike, but they have the same value. Now we ask 8 divides into 24 how many times? And of course that's 3, which I'll multiply both top and bottom. And then this top becomes 21 over 24th. And these two fractions are equivalent. Now what we've reached here is two fractions which, although they each were different, at least end up having the same denominator in their equivalent forms. And that's what we're after. And of course, there's nothing restricting this process to just two fractions. We can have 2, 3, or 1,500. The question now is simply this. I'd like to build each of these three so they all end having the same denominator as each other. Our question still is, what's the lowest number that 15, 5, and 6 will divide into? In this case, these still are simple enough that we can just look at each denominator, think just a little bit, and come to the conclusion that it must be 30. Realizing we could have picked 60, we could have picked 90, we could have picked 120, but 30 is the lowest. So we can build each of these into 30ths. And to do that, we ask 15 divides into 30 how many times? That's 2. So we build this fraction by multiplying top and bottom by 2 into 4 30ths. And so on down the line. 5 goes into 36 times, so we build this fraction by 6 and get 42 30ths. Now note that this fraction is an improper fraction and these two were proper. Proper, improper has nothing to do with this process. It's simply getting common denominators through the act of fraction building. And so continuing this process, 6 goes into 35 times. We build the fraction by multiplying top and bottom by 5, thus getting 25 30ths. So these three fractions, if we wish, may be replaced by these three because they are equivalent. And in the next 2 or 3 lessons, that's exactly what we'll do. Now notice the process wouldn't be changed if I stuck on a couple more fractions. We might have to think a little bit harder to find that lowest number that all of these will divide into. And again, remember from chapter 2, what we're really asking here regarding these three numbers, the fact that they're bottoms of fractions has nothing to do with it. They're simply three numbers, and we're asking what's the lowest number that each of these three will divide into, and that's 30. So in short, we're asking for the least common multiple of and this was the whole business of chapter 2, wasn't it? What happens if these denominators or these three numbers are so complicated that you just can't look and see that it's 30? This brings us to the last and final conclusion of the review we've been playing with over the last 3 or 4 lessons. That business of finally coming to grips with being able to comfortably find the least common multiple of a series of numbers, whether it's 2 or 3 or 15,000. For example, What if we had these three much more complicated fractions and we wish to build each of them so that we have three fractions, each equivalent to these three, but all having the same denominator? Again, we're asking what's the lowest number that 72, 27, and 32 will each divide into. Now note, what the numerator is has nothing to do with this. At this stage, we're looking only at the bottoms as though they existed in their own right, without the tops even. That is, what is the least common multiple of these particular three numbers? Now we must dip back and ask, do you finally recall all the procedures from Chapter 2 for finding the least common multiples of a series of numbers? We have reached the point now where we can't play with that anymore. We must have it nailed down. So for one last effort, let's go back and review the rules we had from Chapter 2 on finding the least common multiple of a series of numbers. To recall those, here's our numbers. The first thing we want to do is to prime factor each number and write in exponent form. Let's do that. 32. Well, we can see that the lowest prime number that will divide into 32 is 2. Goes in 16 times. 2 will still divide into 16 8 times. 2 will still divide into 8 4 times. 2 still goes into 4 twice. So now we can claim 2 times 2 times 2 times 2 times 2 is 32. Since we have 5 2's being multiplied, we write that in exponent form. So we say that 32 in prime factored form is 2 to the 5th. It's important to recall at this stage that this is another way of saying 32. Now let's prime factor 27 in the same manner. Looking at 27, the lowest prime number that will divide 27, we can see is 3. Goes in 9 times. 3 still divides into 9 3 times, until finally all of my divisors are prime numbers. And I have 3 3's being multiplied. Hence I can say 3 to the 3rd power is another way of saying 27. Now, how about 72? Well, we can see because it's even that certainly the prime number 2 divides into it 36 times. 2 still goes into 36. 18 times. 2 still goes into 18. 9 times. Now 3 divides into 9 3 times. So I finally have a series of prime number divisors. So I have prime factored it. I have 3 2's, which I can write 2 to the 3rd power, and 2 3's, which I can write as 3 to the 2nd power. So 72 may be written as 2 cubed times 3 squared. So each of these numbers have been prime factored and written in exponent form. It's important to realize two things. First, that these are replacements for these numbers, simply a different way of writing the same number. Secondly, as these numbers become rather large, this can be a rather long, involved, time-consuming process. We'll accept that fact. So be it. It must be done. So each of these numbers, which were denominators, have been prime factored and written in exponent form. The next thing we want to do, write down each different base for factors to be. Now, what do we mean by that? Well, we can see I used the base 2. 3 is a different base. 2 is used already. 3 is used already. And it's said for factors to be, which means when I'm done, I'm going to be multiplying something. Now, multiplying what? Just 2 times 3? The answer is no. We want to give to each of these bases now an exponent. What exponent? Give to each of the base we just wrote down its highest exponents from our prime factorization. So the highest exponent on 2, well, let's see, it's 5 there and 3 there, so 5 is the highest. The highest exponent on 3, well, it's 3 there, 2 there, so it's 3. This number is the lowest common multiple, and in the case of fractions, our lowest common denominator as well. All we have to do is multiply this out if that's what we choose to do. In this case, let's do that. Later, we'll show you a slight shortcut. But let's keep our understanding clear at this stage. So this is 5 2's being multiplied, which is 32. This is 3 times 3 times 3, which is 27. And 32 times 27 is 864. So we're saying that the lowest common denominator of these 3 fractions would have been 864. Since we're running short on time here, let's do some calculator work at this point. We are claiming that each of these denominators, or each of these fractions, can be changed into equivalent fractions, all with a denominator of 864. Well, using the calculator, we're asking 864 divided by 5, 32 rather, is what? That's 27, which tells me here to build the fraction, I'd have to multiply top and bottom by 27. So if I do this, I should get 864, which I will. So I multiply the top times 27, and it becomes 135. And so on right down the line. 864 divided by 27 goes in 32. So we're going to build this fraction by 32. And of course, multiplying the 2 on the bottom should give me 864, which is a nice check. Then multiplying 32 times the top, I get the new numerator of 224. And so on right down the line for all the fractions that we have. This denominator divided into 864, so 864 divided by 72 equals 12. So I must build this one by 12. So 11 times 12 on top gives me 132. And of course, as a check, 72 times 12 does indeed give me the denominator. So now these 3 fractions have been built into 3 equivalent fractions, which now have common denominators. We'll be coming back to this many, many times, but at this point, it must finally be memorized. This is your host, Bob Thinnell. Until your next lesson, good luck.